We're talking about inverses today. So you did some of this in Algebra 2, but we're definitely doing more with it than you did then. So we know that if something is a function, that means the x never repeats. If something is one-to-one, that means y never repeats. So if it's one-to-one, y never repeats. If you have two different inputs, they give you two different outputs. So two different x values have to give you different y values. So the first thing we're going to do is just look at some different way functions can be represented and decide if each of these is one-to-one. So would this one be one-to-one? No. Why? So these are like my x's and my y's, and we see that y value gets repeated. So it is not one-to-one. What about B? Yes. The shorthand for one-to-one is 1-1, so I'll write that a lot of times. Algebraically, to decide if something is one-to-one, it's kind of a weird approach, but what we do is we will prove that if the y's are equal, then the x's have to be equal. So we'll start out, if my function is like x minus 4, we would do an f of a equals f of b. Okay, that means the y value when you plug in an a equals the y value when you plugged in a b. So one-to-one means the y doesn't repeat. So we basically start out saying the y does repeat. And if I'm solving this for a, if I add 4 to each side, I get a equals b. So what that tells me is if the y values were the same, my x's had to be the same to start with. And if you solve and get a equals b, that means it is one-to-one. If you get anything else, a equals plus or minus b, or a equals b minus 4, or anything like that, then it would not be one-to-one. So let's try a couple. So if I want to decide if this is one-to-one, what we have to do is assume f of a equals f of b. So assuming it's not one-to-one, the y values are the same. So f of a is what you get when you plug in an a for your x. F of b, we plug a b in for the x. So if we subtract our 7, divide by -3, you get a equals b. So that means the only way the y values are the same would be if those x's were the same to begin with. So that means it is one-to-one. All right. So for this one, f of a equals f of b. So f of a is the square root of 49 minus a squared. F of b is the square root of 49 minus b squared. What would you do on this one? Opposite of a square root is? So if I square on each side, then what would we do? And we could divide by -1. We get a squared equals b squared. To get rid of a square, and anytime you add a square root, you have to do. So you get a equals plus or minus b. So that means if y is the same, it could be that a and b with the same x values, or it could be opposite. I could plug in a positive 7 and a negative 7 and get the same answer.
Is it all so plus or minus a?
Yes, you just technically only have to put it on one side.
But if it was on both sides, would it not cancel out?
It does kind of. So if you put it on both, so that means positive a could equal positive b, negative a could equal positive b, positive a could equal negative b, negative a could equal negative b. And so you see these are really the same thing if you divide it by negative 1. And these two are really the same thing if you divide by negative 1. So it's not wrong to put it on both, it just gives you the same answer multiple times. So since I didn't just get an a equals b, this means it is not 1-to-1. So we can always tell by looking at that function. The other option, we know that when we talked about if something was a function or not, x couldn't repeat. And when we looked at a graph, we said, well, if x never repeats, it would pass the vertical line test. 1-to-1 says y doesn't repeat. So to look at a graph, we could check to see if it passed the horizontal line test. So horizontal line test basically says if it's 1-to-1, no matter where you draw the horizontal line, it can only hit the graph once. If there is any horizontal line that would hit that graph more than one time, it would not be 1-to-1. So take a second, sketch those graphs for me, and decide if this would be 1-to-1 or not. So is x squared 1-to-1? No, you can draw a lot of horizontal lines that hit that graph multiple times. What about x cubed? Yes, no matter where you draw that horizontal line, it only hits the graph once. So much easier to look at a graph than doing the algebraic approach, but sometimes it's hard to graph something, so that's why we have the other option. The graph on B kind of illustrates this property. If your function is always increasing or always decreasing, so if it never changes direction, it will have to be 1-to-1. The things that make something not 1-to-1 is if it's increasing and it switches to decreasing in the middle or something like that. That's when we get problems. Now, if a function is 1-to-1, then we can find the inverse, which is our main goal for today. Inverses are like the opposite of something. So if I said I'm going to add 4, what's the inverse of adding 4? Subtracting 4. Okay, if you do both operations, you get what you started with. So if I do 5 plus 4 and then subtract 4, I'm back to 5. They undo each other. In terms of like ordered pairs or the graph, what happens is those x and y's reverse each other. The symbol for an inverse is a -1 power. So in this scenario, it doesn't mean 1 over. That f to the -1 means the inverse. So we'll start out with just ordered pairs. If I want the inverse of these, all we have to do is go through and flip the orders of these ordered pairs. So the first point would become -27, -3. We're not changing the sign, just the order. Next one, -8, -2. -1, -1. 0, 0. 1, 1. 8, 2. And 27. So we just flip x and y for each ordered pair. So tell me, what's the inverse of b? So if we look at these, in the original, the domain, those are your x values. What does those become in the inverse, the y's. So those become my range values. So when we find an inverse, the domain and range reverse one another. So domain of the original function is equal to the range of the inverse, and the range of the original becomes the domain in the inverse. That is going to be very useful for us. The other thing I kind of already said, if you do both the function and the operation, they cancel each other out. So the function and the inverse, they cancel each other. So when you compose a function and its inverse, they essentially just cancel. Those f's would drop out and you get what you started with. So if they're inverses, when we compose them, we just get x. All right. So now we're going to start looking at some functions, and we'll begin by just deciding if they're inverses. So what we have to do, if they're inverses, they have to be true opposites of one another. So that means when I compose them, what do we have to get for the answer? So in that case, x. And it's not enough to check one, you actually have to do both. So if we want to verify if they're inverses, we have to do both compositions and see if we get x both times. If one of them turns out to not be x, then you can stop and say they are not inverses. So f composed with g. So g is x cubed. If you plug that into f, f is the cube root of whatever we put in, and we're putting in x cubed. So the cube root of x cubed is x. So it looks like it works. We have to verify the other direction. So g of the cube root of x g is whatever we put in cubed. So the cube root of x cubed is x. So both of these are x, so they are inverses. Which we probably kind of could have guessed anyway, that a cube root and a cube are inverses. But now we have proof. Let's try another. So if I want to decide if these are inverses, we have f of g of x. G of x is a 1 over x minus 1. And I'm plugging that into f. So if I start looking at this, I have 1 over x minus 2. Is there anything I could do to... If you didn't want the fraction in a fraction, one good strategy is to multiply by the denominator, which is x. So I'm just going to multiply top and bottom by x. And that gives me x over 1 minus 2x. But is that what I wanted? No, I wanted plain x. There is no way this is going to turn into plain x. So that means they're not inverses. I don't have to even bother checking the other way. If one of them doesn't equal x, you can just stop and say they're not. Why don't you guys check the next one? Composed with g, you have to take g and put that into f. Three times 1/3 is just 1, so you get x minus 4 plus 4, which is x. So that one looks good, but we can't stop because it is possible for one to work and not the other. So g of 3x plus 4, 1/3 times 3x plus 4 minus 4. So plus 4 and minus 4 drop. So 1/3 times 3x is x. So both of them turned out to be x. So they are inverses. Is that okay? Because when we find inverses, we are reversing x and y. If we look at the graph, they're always going to be symmetric across the line y equals x. So that's like the line of symmetry. For me, I don't even look at it so much as a line of symmetry. If I'm trying to graph, I just reverse ordered pairs. So different ways to think about it. They're symmetric over y equals x, but it might be easier just to graph one and use those ordered pairs to graph the inverse. So if I wanted to graph y equals 3x minus 2. Okay, that's a line. Y-intercept is, slope is 3, so up 3 and over 1. So there's my function. To me, the easiest way to graph the inverse is just to look at these points. This was the point 0, -2. So what point is on the inverse? This is 1, 1. So the inverse is still, and we've got 2 points that we can draw. So that is a very crooked line. So this is my inverse. If you look, the line y equals x, that's 0, 0, 1, 1, -1, -1. You can kind of see if you folded it on that dashed line, assuming my lines were straight, they would overlap themselves. That's kind of the line of symmetry there. So if I asked to graph this inverse, I didn't even give you the equation, but we could find points on it and get our inverse from those. So this is 1, 2. So the inverse would be, we have -1, 0. So the inverse would be 0, -1. So that's the first little section. This is -2, -2. And you can kind of see the line y equals x. Goes through the middle of that if you graphed it. Questions about anything that we've covered so far? The last thing that I want to work on is finding an inverse. So when we find an inverse, there's some very specific steps that we have to do. So first, we always need it to be written with an x and a y. So if it's in function notation, we'll change that f of x back into a y. Then a function flips the x and the y. So we'll interchange our x and y. Basically, where we see an x, we'll put a y. Where we see an x, or a y, we'll put an x. Solve for y, and then the final step, we'll put it back in function notation, but we'll do that f inverse to show that we found the inverse. So these are the 4 steps that we're going to go through. And that's pretty much what we're going to do for the rest of class, is just practice finding those inverses. So, if I want the inverse, first thing is to change the f of x into a y. What's the second step?
Between X and Y.
So this y becomes an x, my x becomes a y. And now we need to solve for y. So we can subtract the 3, divide by 2. Final step, instead of y, what do we put? So that is my inverse. I didn't ask for it on this one, but on a lot of these problems I'm going to be asking for domains and ranges as well. The domain of the original function is the same thing as the range of the inverse. So you can list all 4, but what I usually do is put a D for domain and a subscript of f, so that's the domain of the function. I know that that would be the same as the range of f inverse. So if I look at my original, there were no fractions, no radicals, so what's your domain? The range of the original function is the same as the domain of the inverse. It is a lot harder to look at an equation and know what the range will be, but we can find the domain of an inverse pretty easily. So if I look at my inverse, it has a fraction. We know that in a fraction, the bottom can't be 0. Does 2 ever equal 0? So it's negative infinity to positive infinity. Let's try some more. First step, instead of f of x, we write y. Then, so y becomes an x. We had 2 x's to begin with, so now we have 2 y's. Okay, we have to solve for y. So first, if I want to get rid of my fraction, I can multiply this y minus 1 over. Xy minus x equals 2y plus 1. What now? What are we trying to solve for? Okay, we have 2 y's. Are they like terms? Can I combine them? No. So let's just get them on one side together and everything without a y on the other. So basically going to subtract over this 2y and add over this x. So xy minus 2y plus 1 plus x. Since both of these have a y, what can we do? And now what do we do? So my inverse is 1 plus x over x minus 2. So if I ask for domains and ranges, Please make sure you're putting subscripts on there. Don't just say D equals F or D equals R. I need to know it's the domain of the original function is equal to the range of the inverse. So if I look back at my original problem, what could x not be? One. The original couldn't be one. So that would be a negative infinity to one, union one to infinity. Now, the range of the original function is harder to find, but I know that is the same as the domain of the inverse. So if you look at the inverse, what can x not be? 2. So that one would be negative infinity to 2, union 2 to infinity. Is that one okay? I think I'm going to change the next problem. I want to give you another one of these fractions. They're probably the hardest ones that we can do, so I want to make sure you can handle one of those. So let's say see if you can find the inverse domain and range. Look at it. So you switch, so you end up with 1x and 2y's. You want to get rid of the fraction, so you multiply the denominator over. Is this okay? So now we need our y's on the same side, so I'm going to subtract over this y and subtract my 3x. Okay. Remember, we're trying to solve for y. So what could we do now? And then what do we do? Okay, so our inverse, instead of y, we write f inverse of x. Now, if you had 5 plus 3x over 1 minus 2x, that's equivalent. We know the domain of the function is equal to the range of the inverse. Range of the function equals the domain of the inverse. So if we look at the original, the domain of the original, what could x not be? Right, we know that denominator can't be 0. So x couldn't be negative 3 halves. So the original domain was negative infinity to negative 3 halves. Union negative 3 halves to positive 50. For the inverse, we look, the denominator can't be 0, so x can't be 1 half. So negative infinity to 1 half, union 1 half to infinity. Any questions there? Last one for today. So I told you that only one-to-one functions have inverses. Here's why. We looked at x squared earlier and we said that wasn't one-to-one, right? Looked like this, it failed the horizontal line test. If you tried to graph the inverse just by flipping all those order pairs, what happens is it looks like this. And what's true about that black graph that I just drew? It's not a function. So in order to be able to find the inverse, it has to be 1-to-1 to begin with. And we know x squared isn't. However, this one I'm throwing in a stipulation that x is greater than 0. So if you think about the x squared graph, but if you're only plugging in positive numbers, is that portion 1-to-1? Yes. So since I'm not taking the entire x squared graph, we could find an inverse for just that part. So we have y equals x squared. Flip the x and y. To get rid of a square root, or of a square, we would square root. And with that, we would typically do plus and minus. However, we already know x and y were both positives. So do I need to worry about the negatives? No. So that means y is just the square root of x. So the inverse is the square root of x. So if I give you a function that's not 1-to-1, the only way we can find the inverse is if I restrict it and only look at part of the domain. All right. So tomorrow is a work day. So these EOE means every other even, so it'd be like 4, skip 6, 8, so forth. So you will have class tomorrow to work on these. If you want to start, you're welcome to do so. That part's up to you.